In this lesson, we're going to talk about lesson number 5, multiple conversions between moles. So that means we can convert between mass, volume, particles, as long as we convert to moles. It's almost like our base unit in a sense. So what have we done so far? Well, we've learned how to convert between the following: moles and mass. We learned how to convert between moles and volume. And we've learned how to convert between moles and particles. And each one uses a different thing. Mass is for molar mass. So if we know the molar mass, we convert between them. Volume is STP. And then particle is Avogadro's number. And what do you notice? Each one of them is related to moles. In a sense, as long as we get to moles, we can convert to any other of the other units. Convert to moles to convert between them. It is like our base unit. And here's a trusty little what we call mole map to help you out. You see how moles in the middle, mass, volume, and stuff, which is particles, is on either sides. In order to get from mass to volume, you first have to convert mass to moles using molar mass. Then convert moles to volume using STP. And if you want to convert from particles to mass, you first use Avogadro's number to get to moles, then moles using molar mass to get to mass. So that is what we call a mole map. Alright? So, how do we convert using multiple conversions? Well, it's quite simple actually. First step, from mass, volume, or particle, convert to moles first. Okay, step 2. From moles, convert to mass, volume, particles. So it's just really 2 steps. It's knowing about where and what you need to convert. So let's take a look. What is the volume occupied by 75 grams of CO2 at STP? So currently we're at mass. That's a mass. And we want to get to volume. So in order to do that, we first had to get to moles. So how do you get from mass to moles? Well, looking at this chart here, you're at mass, you get to moles, use the molar mass of CO2. Okay, so the molar mass of CO2, if you were to find it, it should be 44.0 grams per mole. Okay, so looking at that then, you have 75.0 grams times, we want to cancel out grams, so we should have moles on top, 44.0 grams on the bottom, because that will cancel my grams. And then I now multiply my moles, because I'm currently at moles, I don't get to volume, I use STP. So that is 22.7 liters per 1 mole. And that will cancel out my moles. And now I'm in the unit of liters. So now I can punch this on my calculator to calculate what is that volume of 75 grams of CO2 at STP. So I have 75 divided by 44 times 22.7. And I get 38, well, I want to round it to 3 sig figs, 38.7 liters of CO2. Alright, let's look at the next example. What is a mass of 2 times 10 to the 20 atoms of carbon? Well, let's take a look. Our first step is we are currently in particles. This is a particle. Okay, and we want to get to mass. So what do we do? Well, we're at particles. We got to use Avogadro's number to get to moles, and then using the molar mass to get to mass. So let's try it out. We have 2.00 times 10 to the 20 atoms. Our first step, Avogadro's number to get to moles. So 1 mole over 6.02 times 10 to the 23 atoms. And that will cancel out my atoms. My next step, multiply by the molar mass of carbon. The molar mass of carbon is 12. So we gotta multiply by 12 grams per mole. And as you see, the moles will cancel out. So I'm left with my final answer, whatever that is. 2 times 10 to the power of 20 divided by 6.02 times 10 to the power of 23 times 12. And I'm going to get 0, so 3 safe figs, 0.00399. 0.00399 grams. So you can write it like that, or you can write it as 3.99 times 10 to the power of negative 3 grams. That is your other option. Alright, let's look at example number 3. In example number 3, we're trying to find how many oxygen atoms are 125 liters of SO2 gas at STP. Well, first of all, SO2, that's a molecule. And we want to find oxygen atoms, because in SO2, the molecule, there are 2 oxygen atoms for each molecule. So our species is SO2, but we want to solve for oxygen atoms. Okay, so you're at STP, 125.0 liters. Our first step is, let's get to moles. Whenever you're giving any value, convert it to moles. So to get to moles, use STP, because it's a STP, 22.7 liters. Okay, my next step, I'm at moles. I gotta use Avogadro's number to get to SO2 molecules. So I can only convert to SO2 molecules first. I cannot convert to oxygen atoms because the species I'm dealing with is a molecule right now. So 6.02 times 10 to the 23 SO2s per 1 mole. So I'm currently still only in SO2. Well, in one SO2, how many oxygen atoms are there? There's 2 oxygens per 1 SO2. So that way my SO2s cancel out. And now I can find out how many oxygen atoms there are in 125 liters. So what I have here is, if I scroll this up just slightly so you can see it, what I have here is, I have 125 divided by 22.7 times 6.02 times 10 to the power of 23, okay, times 2. And what I'm going to get here is I'm going to get 6.62, or in this case 6.630 times 10 to the power of 24. So 6.630 times 10 to the power of 24 oxygens. Okay, so that is how we solve for this case. We gotta make sure we know in one molecule there's 2 oxygens in this case, because the species you're talking about is a molecule. Then how does density relate to this? Well, so far in everything we talked about, in order to calculate from moles to volume, we use STP. So far, to get from volume to moles, we use STP. But there's some limitations. STP is only for gases. So what happens if you have a gas that is not a STP? Or what if you have a solid? What happens if you have a liquid? In this case, we can't use STP anymore. We use density for solids and liquids. Okay, because how does that work? Well, density relates volume with mass. So what you're going to do is, with this conversion table we're talking about here, the mole map, density actually sits around out here, where once you have some volume of some solid or liquid, you could use density to convert it to mass, then to moles. So what you got to do is use density to convert volume of solid or liquid to mass, then use mole map. Okay, so we gotta use density to convert our mass to our volume to a mass. So remember, with this, STP can only work for a gas. So let's take a look at this. What volume is occupied by 5 moles of vinegar? Okay, so that means we're currently at moles. We want to get to volume of vinegar. Vinegar is a liquid. So we got to convert this moles to mass first. Then we can use density to get to volume of vinegar. So let's take a look. We have 5 moles of vinegar. To get to moles from moles to mass, we got to use the molar mass of vinegar. The molar mass of vinegar, if I look at it, I have 2 carbons, so 2 times 12 is 24, plus 2, let's see, 2 times that is 24. Let me add these up. Okay, so 2 times 12, 2 carbons is 24, plus 4 hydrogens, each hydrogen is 1, so plus 4, plus 2 oxygens, each oxygen is 16, so it's 32. We get a molar mass of 60 grams per mole. So we have 60.0 grams per 1 mole of acetic acid or vinegar. Okay, we're at grams now. Now we can get to volume. So now I multiply using density, where I have 1 milliliter over 1.05 grams. And my grams will cancel out. So now I can solve for my answer in milliliters. So 5 times 60 divided by 1.05, and I'm going to get, in 3 sig figs, 286 milliliters. 286 milliliters as my solution. Okay. How many moles of bromine liquid are contained in 250 milliliters of bromine? Alright, so one of the things we got to change with this question, though, is that bromine is actually what we call a diatomic. Diatomics means they can only exist in pairs in nature, so this actually should be Br2. That's why this should be Br2 as well. Okay? So diatomics are things that can only exist in pairs in nature. So we have 250 milliliters of bromine. Our first step, we want to solve for mass. Because we can't get from volume to moles yet because we're stuck at mass. So we got to get to mass first. So we got to use density to get to mass. We find that 3.10 grams per 1 milliliter is the density of bromine. Okay. And from here, we now can multiply by the molar mass of bromine to get to moles. The molar mass of bromine is, well, one bromine is 79.9. 2 bromines is going to be, based on this, 159.8. So 159.8 grams is in 1 mole of bromine. So now we can solve for how many moles of bromine we have. 250 times 3.1 divided by 159.8. And we're going to get, in this case, 2 sig figs, because this value is 2 sig figs, 4.8. 4.8 moles of bromine is present. Okay, let's look at our next example. What is the density of nitrogen gas at STP? So we're trying to find density. We know that density is equal to mass over volume. Do we have the mass of nitrogen gas? No, we don't. Do we have the volume of nitrogen gas? We actually do. We know it's at STP. So we know STP is 22.7 liters per mole. Okay, where can we get mass then? Well, we know that nitrogen has a molar mass, which is, in this case, the molar mass of nitrogen is going to be 14 times 2, because it's N2. It's going to be 28 grams per mole. Okay, so what can we do? Well, we can actually take the mass and divide it by its volume. And by doing that, let's see what happens. So we have 28.0 grams over mole, and we divide by this value. Now, you gotta remember something. When we divide by a fraction, what we do is we take the reciprocal of this. So we flip it around and we multiply. So what we get here is we get 28.0 grams per mole times 1 mole over 22.7 liters. Okay. And what we're going to get is, if we were to cancel now, moles cancel out, we're going to get the density of our substance of N2. 28 divided by 22.7, we're going to get 1.233. So I'm just going to round it to 4 digits. 1.233 grams per liter. So it's approximately, as we can see here, 1.233 grams for every liter of nitrogen gas. And that's our density. So let's finish up our last few questions and then we're finished for this lesson, okay? So in this one, we have 5-liter bulb contains 29.3 grams of gas at STP. What is the molar mass of this gas? What is the identity of this gas? Okay. So this question here, we want to solve for what is the identity of this gas, or what do you think it will be? So we know that molar mass has this equation. It is grams per mole. Okay. So where can we get our grams from? Well, we know this is our grams right there. That's our grams. But we don't have anything for moles because we don't know what this gas is. But we do know it's at STP and there's 5 liters of it. We could find moles from that. So if we have 5.00 liters times 1 mole over 22.7 liters, we can actually solve for our moles here. In this case, how many moles of this gas do we actually have? 5 divided by 22.7, we're going to get 0.2203 mole of this gas. And it has a mass of 29.3, so we can find our molar mass. The molar mass is equal to 29.3 grams divided by 0.2203 moles. And this should give you the molar mass of the substance, whatever it is. So if I punch in my calculator, 29.3 divided by 0.2203, I'm going to get 133 grams per mole. Now, what gas may have this molar mass? Well, if we look at our periodic table, we see that cesium can have that molar mass. Cesium is 132.9, but cesium is actually not a gas. It's a solid, it's a metal. So the only gas that's pretty close to it is xenon. Xenon has a molar mass of 131. So it's actually fairly close to that value. So it can be xenon. Our last example here is Fe2O3 has a density of 5.242 grams per milliliter. How many atoms of Fe are present? 200.0 milliliters of Fe2O3. Okay, so we have 200 milliliters of Fe2O3. We're at volume. Volume is right here. We have to get to mass. Alright, so how do we get to mass? We gotta use density. So let's solve for density here. Alright, so let's use density now to solve for our mass. So we have 5.242 grams per milliliter. That is our density, and that will cancel my milliliters. Now I'm at mass. Now my next job is to find and use the molar mass of Fe2O3. The molar mass of Fe2O3, let's go find it up. So we have 2 Fe's. 2 Fe's is 55.8 times 2, and I have 3 oxygens, plus 3 times 16 is equal to 159.6 is the molar mass. 159.6 grams per mole. So now I can multiply by, in this case, 1 mole over 159.6 grams. In this case, my grams will cancel out. My next step now is that I need to get to the number of molecules of Fe2O3. How many molecules are there? Well, we know that per mole we have Avogadro's number of 6.02 times 10 to the 23 Fe2O3 over 1 mole. That will cancel my moles. My last step is, well, how many Fe atoms are in one molecule of Fe2O3? And there are 2 Fe's per 1 Fe2O3. And that will cancel out my Fe2O3. So what would I get as my final answer? Well, let's take a look. You have 200 times 5.242 divided by 159.6 times 6.0, oops, no, it messed up. 200 times 5.242 divided by 159.6 times 6.02 times 10 to the power of 23 times 2. And we're going to get a value of 1, 2, 3, 4, 5, 6, 7, 8. 7.909. 0.909 times 10 to the power of 24 Fe atoms. So we're going to have a lot of Fe atoms present. Alright. So, as always, make sure you keep yourself safe and healthy, and I'll see you soon.